Hi there, this is Professor Shannon Gracey from Costa College. Today we're going to be talking about section 5.1 from the Larson and Edwards Calculus text. This section covers the natural logarithmic function differentiation. So I cannot express how important it is for you to really understand not only the things from chapters 2 and 4, but chapter 5, when you go to calculus 2, is absolutely imperative. You'll be covering the derivatives and antiderivatives of transcendental functions. So here we go. Basically, let's get warmed up by using the limit definition of the derivative to find the derivative of f at x is 3 over x with respect to x. So the limit definition of the derivative, do you guys remember that? So here, let's see what we have going on. In general, the limit definition of the derivative gives us that f prime at x is equal to the limit as delta x approaches 0 of f at x plus delta x minus f at x all over delta x. So, plugging in what we have, we will get that f prime at x is equal to the limit as delta x approaches 0, and we'll have 3 over x plus delta x minus 3 over x all over delta x. So, getting a common denominator, we'll get that f prime of x is equal to the limit as delta x approaches 0 of. So here we need to have an x plus delta x for this fraction to get a common denominator, and over here we're going to need x over x to get our common denominator. Oops, and I forgot my delta x over here. So we'll now have 3x minus 3x minus 3 delta x all over x times x plus delta x, and then I'm going to multiply by 1 over delta x so that we represent this being divided by delta x. Okay, so we will have f prime at x is the limit as delta x approaches 0 of negative 3 delta x divided by x times x plus delta x times 1 over delta x. So these delta x's will divide out to be 1, and then we will have f prime at x is equal to, using direct substitution, I'll just put the result. So we're going to have negative 3 divided by x times x plus 0. So I'm plugging in delta x was approaching 0, so in for delta x I'm putting 0 now that I've divided out and it's not indeterminate. And so this gives us that f prime at x will be negative 3 over x squared. Good so far? Okie dokie. Now let's graph y is equal to natural log of x. So here what we have going on is, let's get a grid here. Okay, so this would be our x and our y, and we can have this just be plus or minus 10, and then graphing. If you start with I don't know, just a chart, if you've got x, y is natural log at x, and then your ordered pair x and y, there's some, important values. So if x is e, y is equal to natural log at e, which is just 1. So you have the ordered pair e, comma 1, e, comma 1. And another interesting value would be what? If x is 1, y is natural log at 1, which is, so remember, if you have this, natural log at x means the power to which I raise e, because that's the base of the natural log, to get x. So basically the output of a natural log function is an exponent. All right? So the power to which I raise e to get 1 is going to be 0. Good, so you have the ordered pair 1, 0. So here, if we plot those, 1, 0, e is approximately 2.72 something, I think. We'll just call it 2.7, comma 1. So 2.7, comma 1 is somewhere around here. And so it's going to look something like this, something like this. So the domain is from 0 to infinity non-inclusive, and the range is from minus infinity to infinity. Okay? All right. So now if we take a look at the definition of the logarithmic function base e, right? So if a is a positive real number where it's not equal to 1, and x is any positive real number, then the logarithmic function to the base e is defined as log base e at x. Now the number e can be defined as a limit. All right, specifically that limit is the limit as some v approaches 0 of 1 plus v, that quantity raised to the 1 over v. So the natural logarithmic function and the natural exponential function turn out to be inverses of each other. So if we go through and copy this graph, right? And we can take a look at copy this guy. Whoops. Uh-oh. Okay, so basically this was we'll have this blue function be f of x is natural log at x, all right, which is equivalent, by the way, to log base e at x. But we have it's so special, we have a special notation for it. And if we take a look at f inverse, right, basically with inverse functions what happens is they reflect across the line y equals x. So this is the line y is x, okay? And so if we did our inverse function, what would happen is instead of the ordered pair at 1, 0, we'd have an ordered pair at 0, 1. And then as opposed to an ordered pair at approximately 2.7, 1, we'd be at 1, 2.7. So do you see that reflection? So basically what happens is you end up with a graph something like this, right? Where this is, you know, some g of x, call it f inverse at x equals e to the x, right? So that's what that one looks like. And this is, call this f at x, okay? Now, the domain that we talked about, that first domain and range, corresponded to f at x. And what would the domain and range of the inverse be? So the domain of the inverse would be, good, it would be from minus infinity to infinity. And the range is what? Beautiful. From 0 to infinity, non-inclusive. So do you see that they flip, right? The domain and range of our inverse function flipped, okay, from our original. Meaning that the domain of the inverse is the range of the original, and the range of the inverse was the domain of the original. So basically, you get this property, right? Natural log at some x equals to y if and only if, that's what the IFF means, e to the y is equal to x. So just keep that one in mind. Okay, so properties, oh, I did it the other way around. So properties of inverse function. Y is e to the x if and only if, what? So a logarithm is an exponent, right? So if and only if the natural log, which takes care of our log base e, right, of at x is equal, whoops, sorry, a logarithm is an exponent, so that'd be natural log at y is equal to x. So I have them switched from here, all right? Okay, so now if you evaluate a function at its inverse, you get what's inside here, right? So this ends up being x, as long as x is greater than 0 to have our domain okay. And then again, we're evaluating the exponential, the natural exponential function e to the x at the natural log function base, which is base e. So we just get what's in the power, which is x for all x. All right, now properties of natural logs. You know, remember, so this is the power to which I raise e to get 1 is 0. The power to which I raise e to get e is 1. It turns out that the log of a product is the sum of the logs, because a logarithm is an exponent, right? A logarithm is an exponent. So remember, if you are multiplying a same base, what do? You perfect, add the exponents. So here, the log of a product is the product of the logs. Same here, the log of a quotient is the difference between the log of the numerator and the log of the denominator. And the log of a quantity raised to a power that's within the log is the power times the log of that quantity. Okay, so the inverse relationship between the natural log function and the natural exponential function can be summarized as follows. So here, the natural log evaluated at the natural exponential function at x is equal to x, and the natural exponential function evaluated at the natural log function at x is equal to x. So we had those problems earlier. Okay. So now let's condense these logarithmic expressions. So if you remember in pre-calculus, this is what you did a lot. You condensed these expressions so that later when you had log equations, you could more easily solve them. So you just make sure you have the same base, right? And so here, this is going to be the natural log at x plus 8 minus, so I have, first I'm going to bring in any powers that we have. So we have natural log at x minus 2, and then we have minus natural log at x to the 5th. So in that last piece, I used the power rule going the other way, going backwards. So this is going to give us the natural log at x plus 8 minus, I have a difference of two logs. So I can rewrite that as a single log of this quotient, x minus 2 divided by x to the 5th. Okay? Now again, I have a difference of logs. So it'll be the natural log of the numerator, right? And then divided by the x minus 2 over x to the 5th. Oops. Now simplifying, let's see, do we have any room? Simplifying, we will have the natural log at x to the 5th times x plus 8 all over x minus 2. And we have condensed this log. All right? Okay, moving along. What do we have? We have a 1/2 power here. So we got to bring that power in. So we'll have natural log at x to the 1/2 plus natural log at z to the 8th, and then minus natural log at y. Now that there's no coefficients, we've written them as powers. What do we have? We have a sum of the first two and then a difference. So let's take it a piece at a time. We'll have natural log at x to the 1/2 times z to the 8th minus natural log at y, and then the natural log of a difference is the log of the quotient. So we'll have natural log at, I'm going to write it as root x times z to the 8th divided by y. And we're all done. Cool so far? All right, perfect. Now, this is what we do more in calculus. We expand log expressions. So here, this can be rewritten as the natural log of all this stuff x squared minus 1 over 2x plus 5. This quantity is being cubed, and this whole thing can be written to the 1/4 because it was a 4th root. Well, this is going to give us the natural log of all this stuff to the 3/4. So now I can bring that 3/4 in front, and I'll have 3/4 times natural log of x squared minus 1 over 2x plus 5. And then separating, I'll have 3/4 times the quantity natural log of x squared minus 1 plus natural log at 2x plus 5. Now it is true that you've got x squared minus 1 is a difference of squares, so you could factor that further, and you could expand it further, but I'm going to show you the things that are going to be the most useful for calculus. Okay? All right, so this next guy, part B, we want to bring that power down. So we'll have, oh, actually, here, there's no log with that one. Do you see that? So this guy, I don't want to just arbitrarily change it, so we're gonna cross this guy out. I probably meant to put natural log of all that. Okay, so here we go. Now, just kind of a note on how another way our natural log function is defined. Okay, so we had our graph, right, of what the natural log looked like. So if we look at this guy again, up here, right? And this was our y and x and our domain and range, and this here was y is natural log at x. Okay. Now, one way that this is defined, okay, is to use the fact that the natural log at some x is equivalent to the integral from 1 to x of 1 over t dt. So it's a little bit different of a visual here. So if you take a look at the difference of a graph of this, what we would have would be you'd have your 1 over t dt is what? It's a hyperbola, right? And so if you were to graph that, and if we were to, let's just do this in terms of x and y, okay? And we're going to graph x and y is going to equal to 1 over x. So here, if we make this, it doesn't have to be really big. Whoops. We'll go scale of 5. So or it'll be a half, right, for each box. So now, if we graph this, and we start at x is 1, we would get an output of 1, right? X is 2, we get an output of a half, and you see it's going to get smaller and smaller and smaller, so we're going to end up, and then over here it's going to increase without bound. So if x is 1/2, you're going to get 1, 2, right? So your graph gets ever closer to the vertical asymptote and to the line y equals 0. Well, if you go ahead and if you were to, take a look at starting at 1, right? So you're going from, you're bounding it here, and you're also going to bound using the or the x-axis, the line y is 0. It turns out that your area region, you know, if x is, let's just say x happens to be here, we'll just say this is x, and this was 1, then your area region is going to look like this. Okay, so so basically, if you have natural log at e, right, is going to be equal to the integral from 1 to e of 1 over t dt, right? Well, what is natural log at e? We know that one, right? E is approximately, good, 2.7-ish, right? So that'd be somewhere over here, 2.7-ish. So here, if we bound it with this line too, right? This is basically x is x, this is x is e, and this was x is 1. Then that region under the curve right here, this region right here, equals 1. The area under the curve would equal 1. Okay, because we know natural log e is 1. So this is the way our author will define the natural log function. So now let's take a look. We're going to review, all right, and solve some equations. So remember, when you're solving equations, the trick, logarithmic equations, the trick is usually to condense, and then you either equate the inside of two logs if you have a single log on each side, or you switch it to exponential form, or you can use change of base formula. You know, there's all kinds of techniques. If you're having any trouble, you can go to mathchick.net. In my intermediate algebra class, chapter 12, I believe, I've got full sections of logarithms and their properties, so you can review if you need to. It'll come back to you though. So here, condensing this log, we'll have natural log at x minus 2 times x plus 2, because I have a sum of logs, is equal to 16. So now what I'll have is the natural log of the quantity x squared minus 4 is equal to 16. Remember, the log has a base of e, so I'm changing this. This is true if and only if e to the 16th is equal to x squared minus 4. E to the 16th is equal to x squared minus 4. Okay, so far, because a logarithm is an exponent. So what we have going on is our x squared would equal to 4 plus e to the 16th. And if you square root both sides, right, remember automatically it'll become a plus or minus. So if you square root both sides, we're going to get x is plus or minus the square root of 4 plus e to the 16th. But we have to make sure that we are keeping, you know, in line with our domain. So when you have an equation, you have to consider the original. So I know that you can end up squaring the x, and you know, when you bring them together. But basically, when we're looking at this domain, do you see that what we have in the beginning is that x minus 2 has to be greater than 0, and x plus 2 has to be greater than 0. So x has to be greater than 2, and x has to be greater than negative 2. So we need to figure out, okay, what is the square root? The x greater than 2 part is fine, right, for the positive root of 4 plus e to the 16th. But what we want to make sure of is we want to make sure of second square root quantity. And what was it? It was 4 plus e raised to the 16th. Enter. So that's a pretty big number, right? So here, I'm just going to write down its approximate, it was approximately 2981, I think. Big number, approximately 2,981. So here, so the positive root is just fine, okay? But the negative root, do you see, is not, if it had been less than, if it had been, if you plug that in and check the original equation, the negative won't work. It's extraneous. So our result, our end result, so our negative is extraneous, meaning that it works out algebraically, but it's not the right answer. So we're just going to use the result of the square root of 4 plus e to the 16th. Exactly, right? So this is the exact. And then what did I say? You could round to 3 decimal places. So if we look here, it would be 2980.959. 2580.959. Approximate. Okay, so that's the first one, and again, you can just plug it in to make sure that it works, and go from there. Right? So here we go. Next up, we have an exponential, right? So we want to, you always want to, if you recall, isolate your exponential. So what we'll have is 1/60th equals e raised to the 3t. And then if we natural log both sides, what we'll get is natural log at 1/60th is equal to, we're evaluating the natural log at the exponential, so we just get what's inside that power, 3t. So there's a little trick for the exact. If you write it as natural log at 1 minus natural log at 60 equals 3t, what is natural log at 1? Good, it's 0. So you'd get 0 minus natural log at 60 is 3t. 3t. So negative natural log at 60 is 3t. And dividing both sides by 3, well, I'm going to write it as negative 1/3 times natural log at 60 is equal to t. So that's our exact. Or the approximate, you would have negative 1/3 times natural log at 60. Enter. negative 1.365. 365. And that's approximate. Okay. All right, so the derivative of the natural logarithmic function. So basically, when you think of it in terms of this picture that we drew over here, actually let's just work with this visual. Or we're going to work with this part right here. So it becomes real simple when you just work with that part right there. You basically have, we've said that natural log at x is equal to the definite integral from 1 to x of 1 over t with respect to t. Now, if you recall, we learned something in 4.4 called the second fundamental theorem of calculus, right? Oops. This is supposed to be ddx of both sides, ddx of both sides. So now, what do we get on the left? We get the derivative with respect to x of natural log at x is equal to, so we have a constant going to x. So that second fundamental theorem of calculus tells us that this is just going to be 1 over x. Isn't that pretty cool? Right? It's that easy. So what about if we had where u is some function of x? So I'm using that second fundamental theorem of calculus. So the second fundamental, can I do FTOC? Theorem of calculus said that if you have some capital F of x, right, which is an antiderivative, is equal to the integral from a constant to x of some function of t with respect to t. It said that the derivative with respect to x of both sides gives us capital F prime of x is equal to f evaluated at x. Now, there was another kind of case where if you had something along the lines of capital F of x was equal to a constant to u equal to some function of x, right? And then you have your f at t dt. If you recall, evaluating d dx of both sides, we basically said, hey, this is going to give us our capital F prime of x on the left, but we're going to adjust this a little, and we're going to write this as d du of the integral from a to u, and we're going to have this, our f at t dt, right? But the way that we balanced this out was we multiplied the result by, beautiful, du dx. So see, they're all being multiplied. So do you see that this is still d dx? Okay, it's just written differently. So these guys connect. What if we have d dx of natural log of some function, u is some function of x? We're going to have, writing it as we had before, we're going to have d du of the integral from a to, actually I'll say 1, because we start at 1 to u of 1 over t dt multiplied by du dx. Okay? So that is going to give us a result of d dx of natural log at u is equal to 1 over u times du dx. So different ways you can write this. You could write this as u prime over u if you'd like. Some people do that. And just don't forget to back substitute whatever u was substituting for x. Okay, so here we go. These derivatives. The derivative with respect to x of natural log at x is 1 over x. And over here we just did this one. It's 1 over u times du dx, or u prime over u, however you like it best. So here, sometimes you might want to figure out what your u is. I've had more success writing it a little differently. So let's take a look. I'll show you how I kind of go about this. Now with logarithms, it's also really good to look at it, take an overview of what you have, and then think about, okay, could I simplify this using properties of logs before differentiating? And always think about that. It's worth knowing your properties of logs. So this is going to give us y prime is equal to 1 over what's inside the log. So what's inside there? 5x. And then we're using the chain rule here. So we're going to go times d dx of what was inside, which was 5x. So that, again, it's just really the chain rule. So y prime is going to be, good, 5, because that's the derivative with respect to x of 5x, over 5x, and at the end of the day we would get y prime is 1 over x. Okay, so far? So that's the entire derivative, okay? So the entire derivative is going to be, this, and, we did a piece at a time. So the derivative of that inside, the derivative of that inside function, all of this was just 5. Okay. All right, so next up, let's see what we have going on. We have f at x is natural log at 1 minus 2x. So be careful with your properties of logs, because remember that, I'll rewrite it down here for us. So f of x is natural log at 1 minus 2x. Remember that there's no property for the log of a difference, right? And if you don't believe me, go ahead and look. So we're going to differentiate both sides with respect to x. On the left side, we'll get f prime at x. And on the right side, what's our u? What's inside the log? So we'll have 1 over what's inside the log, which is 1 minus 2x. And then times d dx of that inside, right? Using our chain rule. And so then, what will we get? F prime at x is 1 over 1 minus 2x times negative 2. So this here, d dx of 1 minus 2x is negative 2, and our whole derivative cleaned up is f prime at x is equal to negative 2 over 1 minus 2x. Good so far? Okay. Now sometimes, there's stuff that's a little bit tricky. All right, so this problem here if you thought of this as y equal to natural log at x raised to the x, right? Actually, no, I'm sorry, we don't have to do it that way. I was thinking of a different type. All right, so here, if we differentiate both sides with respect to x, should we do that? I mean, does that help us? No, I mean, maybe we should rewrite this. So f of x, how could we rewrite this? Beautiful, it's x times natural log at x. So now when we differentiate, we're going to be using a combination of, the product rule and your new formula for the derivative of natural log at x. So we'll get f prime at x is equal to 1 times natural log at x plus x times the derivative with respect to x of natural log at x, which is 1 over x. So this here is d dx of natural log at x, and this one right here is d dx of x. So f prime at x will be, we usually write it as 1 plus natural log at x, so there's no confusion. All right. Next up, what might we want to do? I mean, you could differentiate that directly, but when you use the chain rule, it's going to be mean. Why don't we use some properties of logs to clean it up a bit? So this is equivalent to y equals, that it's all in square roots, so isn't that a 1/2 power? So 1/2 times natural log at x squared plus 1 divided by 1 minus x. So that, again, still working with the original, is 1/2 times natural log at x squared plus 1 minus natural log at 1 minus x using the quotient rule. The log of a quotient is the difference of the logs. Now we can differentiate with respect to x. So we will get y prime is equal to 1/2 times. So we'll have, I'm going to write it as d dx of x squared plus 1. So I'm kind of doing it in the let me do that in green. I'm kind of doing this in the u prime over u format. And then that's going to be over x squared plus 1. So that'll be the derivative of the first term in there when we finish. And then minus, we're going to have the derivative with respect to x of what's inside, 1 minus x over 1 minus x. Okay, so far? Good. So y prime will be 1/2 times, perfect, 2x over x squared plus 1 minus -1 over 1 minus x. Now, since it's a derivative, let's go ahead and get a common denominator and simplify and all that good stuff. So this guy, we're going to have y prime is equal to 1/2 times 2x times 1 minus x, because that's what we're missing from that denominator, and then plus 1 times x squared plus 1 all over x squared plus 1 times 1 minus x. Okay, so moving on, we have y prime is 2x minus 2x squared plus x squared plus 1 all over, I'll get that 2 in there, so 2 times x squared plus 1 times 1 minus x. So that'll give us y prime is negative x squared plus 2x plus 1 all over 2 times x squared plus 1 times 1 minus x. And we're done. Good so far? All right. Moving along, here we go. So now we have the natural log at cosine squared at x, which is equivalent to what? Natural log at cosine at x, the quantity squared. So wouldn't it be nice to just write it like this? 2 times natural log at cosine at x, and then differentiate? Also, please, I highly recommend that you pause the movie and try these yourself, so that you're good to go on these. Okay, so we will get dy dx on the left is equal to 2 times. So here's our setup. We're going to have d dx of what's inside the log. What was inside the log was cosine at x, and that's going to be over what's inside the log, cosine at x. So dy dx will be equal to 2 times, good, negative sine at x over cosine at x. But what is that? Perfect. That would be negative 2 times tangent at x. Because remember, the sine function over the cosine function is the tangent function. Awesome. All right. Now, okay, with this one, let's rewrite our equation using the properties of logs as natural log at x plus natural log at y, and then plus x squared minus y equals 10. So differentiating both sides with respect to x, we will have I'm going to go ahead and write a little bit more out for us this time, just in case you forgot. So these all, the derivative with respect to x will go into each term on the left. And then the result of the derivative with respect to x of 10 is 0. So we'll have, good, 1 over x is our first derivative, plus, now this is going to be, this is implicit, so you're going to have d dx of y, green, of y over y when we implicitly differentiate natural log at y. The next one is explicit, so it's just going to be 2x, and then minus, good, dy dx is this guy, and it's all going to equal to 0. So now we'll have 1 over x plus, good, dy dx over y plus 2x minus dy dx is equal to 0. So if I factor out a dy dx on this left side, I would have 1 over y minus 1. And I'm going to go ahead and get the 1 over x and the 2x to the other side. So I'll have minus 1 over x minus 2x. Now before I divide, I'm going to simplify, or before I, yes, divide, I will simplify. So this is going to be dy dx times, I'm basically going to multiply the 1 by y over y for the first part. So I'll have 1 minus y over y, and that's going to equal to, over here, I'm going to multiply the 2x by x over x, and I'll get a negative 1 minus 2x squared over x, and I just pulled the negative to the outside. So now, inverting and multiplying, I can isolate dy dx, and I will get negative y times 1 minus 2x squared over x times 1 minus y. And that's it. We're all done. Good so far? Beautiful. All right. So now we have a theorem involving the absolute value of the derivative involving absolute value. So if u is a differentiable function of x such that u is not equal to 0, then the natural log at the absolute value of u, the derivative with respect to x of this, is equal to, good, natural log, or nope, sorry, is going to end up being 1 over u times du dx, or just u prime over u. It's the same. All right. So here, for the proof of that, let u be greater than 0. Okay? And recall that the absolute value of u is either going to be negative u for u less than 0, positive u for u greater than 0. Right? So if u is greater than 0, then we would have d dx of natural log at absolute u would equal to d dx of u, which is equal to, from before, good, u prime over u, and we're done. Now, case 2, let u be less than 0. So then d dx of natural log absolute u would equal to d dx of natural log of negative u, which would be d dx of negative u over negative u, which is negative 1 over negative u times du dx, so that negative 1 du dx is from the negative u, which gives us u prime over u, and we're done. Okay? All right, so now let's find the derivative of the following function with respect to x. So, differentiating with respect to x, we will get f prime at x is equal to let me do it how I've been, d dx of secant at x plus tangent at x divided by secant at x plus tangent at x. So f prime at x will be the derivative with respect to x of secant at x is secant at x times tangent at x. The derivative with respect to x of tangent at x is secant squared at x, and that's all over secant at x plus tangent at x. And I'm sure there's more, algebra or trig stuff that you can do to simplify that a bit more, but we're good for right now. Okay, so now let's differentiate these things with respect to x. Now this, by the way, is where we're covering something called logarithmic differentiation. And basically, you're allowed to, differentiation. You're allowed to evaluate the log of differentiation. You're allowed to evaluate the log of both sides of an equation. So if we were to let y equal to x squared times x plus 1 times x plus 2, all raised to the 1/2, and we evaluated the natural log of both sides, we could then write this as natural log at y is equal to 1/2 times. So we'll have natural log at x squared plus natural log at x plus 1 plus natural log at x plus 2 using properties of logs. So now you can differentiate with respect to x, but you have to remember that the left side is going to be implicit differentiation. So here we're going to get d dx of y over y equals 1/2 times, and then going through and differentiating each term, so this guy is x squared, it'll be over x squared. This guy is x plus 1, and it'll be over x plus 1, and this guy is x plus 2, so it'll be over x plus 2. And they were being added. Okay? So now what we're going to get is we're going to get dy dx times 1 over y is equal to 1/2 times 2x over x squared plus 1 over x plus 1 plus 1 over x plus 2. Now if we multiply both sides by y, what will happen is this. We will get these y's will divide out. We're going to get our dy dx isolated, which is nice. And then we're going to have y over 2 from the 1/2 times the y. We're also going to get a common denominator. So we'll have 2x times x plus 1 times x plus 2 plus 1 times x squared times x plus 2 plus 1 times x squared times x plus 1, all over x squared times x plus 1 times x plus 2. Okay, so far? So here I'm going to say continued below. So page, append. Okay, so where were we at? I'll go ahead and copy this so we have it to refer to. I was a little crooked, wasn't I? Okay, new. Copy. Paste. Okay, so this was x squared and this was x plus 1. Okay. So this will give us dy dx. Now what was y? So remember that y was, if you go back to the original, okay, y was x, all of those factors inside the square root. So I'm going to write them as x squared times x plus 1 times x plus 2. All of this is to the 1/2 power, okay, over 2 times x squared times x plus 1 times x plus 2. All of these, do you see, are to I can write it to the 1 power since I'm writing them in the denominator. So, and then I still have all this stuff. So that's going to give us 2x times x squared plus 3x plus 2 plus x cubed plus 2x squared plus x cubed plus x squared. Now, working with these guys, so just so you know what to match up, y was all of this from the beginning of the problem. So now I've got the same base, right? So I subtract the exponents. So I'm going to get dy dx, writing it as a positive exponent, will be 1 over 2 times the square root of x squared times x plus 1 times x plus 2, because you would have ended up with a negative 1/2, which is the positive, the square root in the denominator. And then now let's see what we get for this guy. So we'll have 2x cubed plus 6x plus 4 plus 2x cubed plus 3x squared, and we're almost done. Dy dx will be equal to 4x cubed and this would be, this is, 6x squared, and this is 4x. So we'll have 9x squared and then plus 4x all over 2 times the square root of x squared times x plus 1 times x plus 2. And now we may be able to go a little further. Dy dx will be, we can factor out an x. Do you see that? and that'll leave us with 4x squared plus 9x plus 4 over, I'm going to separate this radical. Do you see that I'll have I can write this as 2x to the 1/2 and then times the square root of x plus 1 times x plus 2, and that will give us dy dx is equal to x to the positive 1/2 Actually, you know what, that would just be rationalizing it. Let's, that we've gone far enough. I'm sure you're sick of this problem. Let's just keep it this way. We'll have it as 2 times root x squared times, because it would have been x squared to the 1/2 anyway. Yeah, I don't want to worry about a change in sign. Let's just leave it like this for right now. So this is good enough for the simplification. So I know that didn't really probably seem that much easier to you, but really it could have been a lot worse with the using the chain rule from the original. Okay. All right. So now let's take a look at this guy. So again, evaluating the natural log of both sides, we would get natural log at y is equal to 2/3 times natural log at x squared minus 4 minus natural log at x squared plus 4. Differentiating both sides with respect to x, we will get, good, it's going to be dy dx over y, I'm going to start going a little faster, is equal to 2/3 times, we'll get 2x over x squared minus 4 minus 2x over x squared plus 4. So if we multiply both sides by y, again these y's will divide out, we'll have dy dx is equal to 2y over 3, and then I'm going to simplify the inside. So we'll have 2x times x squared plus 4 minus 2x times x squared minus 4 all over x squared minus 4 times x squared plus 4. So continuing, we will have dy dx is equal to, I'm going to keep the y as it is for right now until we have it simplified. So this is going to give us, we can actually factor out a 2x and we'll get x squared plus 4 minus x squared minus 4 all over, I'm going to just write this as x squared minus 4 over x squared minus 4 times x squared plus 4. Okay, so now dy dx equals, so our original y was, so we have our 2/3, and then y was, if we separate, we've got x squared minus 4 to the positive 2/3, right, over x squared plus 4 to the positive 2/3 using properties of exponents. And then this will be times 2x times the x squareds will zero out, and we'll end up with 16. And that's all over our x squared minus 4 times x squared plus 4. Alright, so combining everything and simplifying, we will have 2x times 16 is 32x, so we'd have 64 x's in the numerator when we multiply by 2. And then in the denominator we will have the 3. X squared minus 4 to the 2/3 minus 1 would give us to the negative 1/3. So we'll have x squared minus 4 to the positive 1/3, writing it in the denominator. And then when I multiply the x squared plus 4 to the 2/3 times x squared plus 4 to the 1, I will get x squared plus 4 to the 5/3. And we're done. Okay? All right. So again, so you can follow, this here is y. Okay, so remember this is, which problem was this one? This was example 6a continued. Is example 6a continued. Alright, so now example 7 calls for us to find an equation of the tangent line of this function. So everything, everything here repeats. So meaning that all the applications apply, everything applies. So let's rewrite f of x. If you recall, we need to differentiate to find the slope of the tangent line. So this is equal to sine at 2x times 2 times natural log at x, using properties of logs. So if I differentiate with respect to x, I'll get f prime at x is equal to, so the derivative of the first one is going to be, beautiful, 2 times, that's the derivative of the angle, so 2 times cosine at 2x, that's the derivative with respect to x of sine at 2x, and then we'll leave this one unchanged, plus sine at 2x times the derivative of 2 times natural log at x, which will be 2 times 1 over x. Very good. So now f prime of x, let's simplify it a little bit. We'll get 4 times cosine at 2x times natural log at x plus 2 over x, or we can say 2 times sine at 2x over x. Alright, so we want to find the equation of the tangent line at the point 1, 0. So we know that this is our x comma x1 y1 or x0 y0, depending on what formula you're using. So we want to know what the derivative is at x is 1. So this would be 4 times cosine at 2, right? Because 2 times 1 is 2. I don't need all these parentheses. I'll just show it. So cosine at 2 times 1, and then times natural log at 1, plus 2 times sine at 2 times 1 over 1. So f prime at 1 is 4 times cosine at 2 times 0 plus 2 times sine at 2. So f prime at 1 ends up just being 2 times sine evaluated at 2. That's the derivative. So when we do the equation of our line, right, we'll just have y minus 0 is the slope, which is 2 times sine at 2 times x minus 1. And then, of course, we could just write that as y is equal to 2 times sine at 2 times x minus 1. And we're all done. And if you need an approximation, you can get an approximation. Alright, so that wraps it up for 5.1. Hope all is going well. Next time we'll be looking at the natural logarithmic function and how we get a result of that when we integrate. Okay? Alright, so have a great day. Bye.